Welcome everybody. Thursday afternoon, IUCAA Colloquium. We've been at this from April, every Thursday, and now every other Thursday. And I'm very glad that a lot of you have stuck with us, and we have a changing bunch of participants both here and on YouTube, where it's being broadcast. Today we are so happy to have Professor Bernard Schutz with us to talk about gravitational wave astronomy. Professor Schutz, of course, is with the grandly named Gravity Exploration Institute at the University of Cardiff. He's been with the University of Cardiff for a long time. Before this, of course, he helped set up the Albert Einstein Institute, one of the Max Planck Institutes in Potsdam in Germany, and he's built a lot of such groups and institutions. He recently got the Royal Astronomical Society's Eddington Medal last year, as you know. We're also very proud to have him be associated with IUCAA for a long time. He's been part of the Scientific Advisory Committee several times. In fact, when we were thinking about building a gravitational wave detector in India from the early days, Professor Schutz was part of that conversation. He was the meeting that set up Indigo, the Indian part of which is now the LIGO Science Collaboration here in IUCAA in 2009. And of course, he's been one of our mentors of the gravitational wave activity, which has now turned into the big dream that we have of building LIGO-India here. So welcome, Professor Schutz. I hand the mic over to you, and what we'll do is we'll do the questions as we do normally at the end, where we'll ask people to use the raise hand option and come and ask questions.
Okay, well, thank you very much for that very kind introduction. I'm very pleased to again be joining my friends at IUCAA. I wish it were in person. I wish I could be enjoying the beautiful facilities and the in-person conversations, but I'm sure that all of us are in that position. We're all having to do things remotely. So at least we have this, and we can talk together this way. So it's as I said, a great pleasure to be talking about this, and also to be talking about gravitational wave astronomy at a time when it has started to bear fruit, and so I would like to give a survey of where we are and what are the interesting things that have been found recently, and what I think are their importances or the significances, and also to have a little bit of a look ahead at what we can be expecting in the near future and the middle term. And I know that many of you in the audience are well versed in what I'm going to be presenting, so I apologize if some of this is already very well known to you, especially those of you who are inside the worldwide LIGO-Virgo upgra collaboration. But nevertheless, I think we can all rejoice in how well things have been going. So let me remind us all that the gravitational wave window on the universe opened up in 2015 with that first detection. And that was right at the beginning. In fact, that kicked off the observing run, 01. And that run lasted for 4 months and garnered 3 events in total that have been identified by LIGO. I'm only going to be using the LIGO identified events. There have been other groups that have gone through the open data and made very good cases for other events, and so I'm not trying to ignore those, but I'm just staying with the LIGO designated events. The first picture on this page is that is the range of the detectors in 01. This is the binary neutron star detection range. Even though we're detecting black holes, it's a measure of the sensitivity of the detectors. So you can see the 2 LIGO detectors, Virgo is not operating, they're around 70 megaparsecs in range. Then 02 began and produced, after an upgrade in sensitivity, produced in 9 months of observing 8 detections. and that included the spectacular binary neutron star merger, GW 170817. And in the picture, you can see that the range of the detectors hasn't increased a huge amount between O1 and O2. Livingston is increasing in sensitivity as time goes on. LIGO Hanford had a problem and dropped down in sensitivity, and then Virgo joined at the end in that spectacular month of August, which produced about half of the detections. So after that, there was another pause for sensitivity upgrade, and then we came to O3, which began last year at the beginning of April. LIGO and Virgo had much improved sensitivities. You can see that the Livingston detector is up, pushing up toward 140, maybe 130, 135 in range. And the Hanford detector is still lagging because of its optical problem. It had a defect in a mirror that had developed, and so its sensitivity was always lower. Of course, that problem is going to be remedied now for the next observing run, and hopefully they'll both be at the same range. And Virgo improved its range to something close to around 45, close to 50. The result was that the detection volume expanded by about a factor of 4 for this network, and that brought in about 39 events in 6 months, which is a rate that went up about 6 times higher. That's it should have gone up at least 4 times higher, but I think it also went up 6 times, a bit higher than that factor 4, because there was more confidence in the detections, and the thresholds could be lowered, or we didn't have to have such good coincidences and so on. The really interesting thing about O3A is the extraordinary way in which the events have been broadened, the nature of the events that we've been detecting. It was already surprising right from the beginning that we had heavy black holes in the very first detection. And that's continued to be the case. But we've seen a lot of systems that are pushing the boundaries and making us rethink things that we thought, other things that we thought weren't going to happen. So I want to be giving you a bit of an overview. The gravitational wave transient catalog, GWTC2, covers the events in O3, tells us about the events in O3. 39 events. On 3 different days, there were 2 events on the same day, and that's led to a change in the nomenclature, broadening the nomenclature. Instead of just giving GW 190421, for example, the date, you have to also give the time of the detection. So that allows us to distinguish events that are happening on the same day. There are 4 events that in this catalog that were so special that they had discovery papers all on their own. And those I'm going to go through each of them. I'm going to give a discussion to each of those events later. But first I want to say just sort of an overview of how we've been pushing the boundaries. So for instance, there's a thing called the lower mass gap, which is between roughly 2.5 solar masses and 5 solar masses for compact objects. It's a bit too heavy for a neutron star and a bit too light for what we expected black holes to be formed at. And so you would, in principle, not expect to find compact objects at all. Well, we've have 2 binaries now with secondaries that have masses in that mass gap. One of them is one of the ones I'm going to be talking about, 1908-14. But there's also 1909-24, 02, 1846. And their secondaries are in that mass gap. And so that's a challenge to try to understand how objects get there. Not impossible, but they were thought to be rare, and they're not so rare. There's also an upper mass gap that astronomers have believed between about 70 and 120 solar masses. One wouldn't expect to find individual black holes because the progenitor stars would suffer an instability that would just explode the star completely and leave no remnant behind at all. But GW 190521, the primary mass, the primary black hole has a mass around 90 solar masses. It's smack in the middle of that mass gap. So there's a big question. How did that star form? And I'll be coming back and talking about that system later on. We've also seen big mass ratios. GW 190814 has the extraordinary big ratio of about 9:1 between its primary and secondary objects. And I'll be talking more about that system. It's a very interesting one. We have been pushing up into the intermediate mass black hole range, and intermediate mass black holes are sort of the boundary between stellar mass and intermediate mass is around 100 or something like that. There's not a great deal of very solid information in astronomy about intermediate mass black holes. It's been a matter of speculation how many of them there might be. Well, we just saw one being made, which was GW 190521. The remnant, the merged remnant, has a mass that's greater than 140 solar masses. That's our best established IMBH. We know that there is at least one intermediate mass black hole in the universe because we saw it being made. But actually, we've seen it happen 3 other times as well. That list of events all are merger events that produced a remnant above 100 solar masses. So we see the intermediate mass black hole range being populated at the low end by mergers of stellar mass black holes. Of course, that doesn't tell us a lot about the rest of the things that might be in that range. The heaviest known binary neutron star system also turned up in our data, GW 190425. I'll be coming back to that. It's heavier than any of the binary pulsars that we know from our own galaxy. And the last thing I want to mention here on this list of boundary pushers is GW 190814, which I mentioned earlier because it has its mass ratio of 9:1. The secondary, that 1, is in the mass gap, and it's it has a nature where it might be a black hole or it might be a neutron star, and we don't really know which it is. So that's a mystery that we may never solve for that particular event because we have all the data we're going to get for that particular system. But it's certainly an active area of research as to how to figure out what that system might have contained. So let's go through and talk about the ones that had their individual detection papers. By the way, these some of them don't have this appendage to their names of the time that they were detected. We're not going back and renaming ones that acquired a name before that convention was changed. Okay, so these ones that have their own papers, their names were fixed before we decided to start adding the time of day to them. So they will keep their standard names. With a mass ratio of about 3:1, this system was the first time we'd seen a binary system where the estimates of the component masses don't overlap at all. As you probably are aware, the component masses are separated from the total mass or from the Chert mass by post-Newtonian parts of the waveform, by observation of the post-Newtonian aspects of the waveform. And so they're not so accurate as other aspects of what we're measuring. And but this one was accurate enough. The ratio was enough, so they were completely separate. So that was the first time we'd seen a really asymmetric system. systems like that are interesting because they radiate with higher multiples than the quadrupole. If you have exactly equal masses, you're only going to get quadrupole radiation. But if you have unequal masses, then you're going to get other multiples in the outgoing radiation. They are important because they have different radiation patterns, different antenna patterns as they radiate. And so, if you can identify the amplitude of a higher multipole and compare it to the amplitude of the quadrupole and combine it with the other information that we're getting at the system, it allows us to get a better idea of the inclination of the system. The inclination of the system to the line of sight is important for estimating the distance, because the distance is a luminosity distance and depends upon the amplitude that we receive. But we have to correct that for inclination effects before we can actually get a good distance. And so if we can measure the inclination better, we can measure the distance better. And this graph shows you the inclination on the horizontal axis and the distance estimate on the vertical axis. And if we just took the quadrupole, that's the blue curve, then the uncertainty region is quite large. The inclination could be almost anything, and the distance could be anything from like 400 to 1100 megaparsecs. If we add in the higher multiples, then we get the dashed line, and then immediately it tells us what the inclination is, that it's face on. It's below. It's between 0 and pi over 2, right about it in the middle. And it gives us a better constraint on the distance. But then also there's evidence for precession in this system. And that also then gives us even more information about directionality and inclination. And we're narrowing down to in the 90% percentile to this orange circle. And that's a much improved distance measurement. It's one of the better distance measurements we have. So that's an interesting system because it was the first time we were able to use these higher multiples. Another system that we thought was worth publishing about was GW 190425. This is the one with the heaviest binary mass neutron star. So the binary system itself has a mass between 3.3 and 3.7 solar masses, and we don't know exactly because modeling it depends upon the spins of the stars because they're close enough for spin-spin interaction and spin-orbit interaction to affect the signal, and therefore the parameters we deduce from it. So in this graph, the two curves I want you to look at first are the ones in color. The orange curve is where the spin parameter is very small, so it's basically two non-spinning objects, and then you can see the mass is well focused on around 3.3. But if we put in a larger spin parameter, and we don't see many neutron stars that are spinning very fast, but nevertheless they might be there, then the PDF widens out, and the mass could be going up to as high as 3.7. So it's a high mass, but the important thing is that we can separate the component masses well enough to know that both of them are below 2.5 solar masses. Both of them are in the neutron star range. So this is a binary neutron star. It's not a black hole neutron star system. It's a binary neutron star system. And then you ask, well, what do we know about the binary neutron stars from our galaxy? And that's what this part of the curve is. The histogram is the histogram of the masses of the combined masses, the total masses of the binary pulsar systems that we know about in our galaxy. And the dashed curve is a Gaussian fit to that. It's not a great fit, but the point is that that's well below, that's completely separated from the PDFs for the mass of this system. So this is way more massive than any binary system that we see in our galaxy. And that raises all sorts of questions about how that might have happened. It's usually the case, it's expected that the first neutron star kind of helps trip the second star, and often, that produces relatively low mass neutron stars, even though the upper mass limit is much higher than we normally see in the galactic binary neutron stars. But so maybe there's a different evolutionary history. Maybe it formed from a triple system. Maybe there was a different kind of evolution history involving a triple, or maybe these were two isolated neutron stars, both of them rather heavy, that met each other in a dense cluster, like a globular cluster, and through dynamical effects, they were captured into orbit around each other. So we don't really know, but all of these questions are new questions that we're trying to understand. GW 190521 is probably my favorite, and probably the favorite for a lot of people. This is the detection picture for the three detectors. And you see there are not many cycles in this detection. That tells you that it's a high mass system, that it's really at the low end of the frequency band of the detectors, just managed to get into the frequency band to be seen. This is our highest total mass system. It's the one that formed the IMBH. The total mass at the beginning was 150 solar masses, consisting of apparently about 85 and 66 solar mass components. It's the most distant system that we've ever detected at a redshift of 0.8. Not surprisingly, it could be very far away if it's that massive, and we could detect it. It's the least talkative, if you like. It's only given us 4 cycles in this information that we got from the waves. And so we've got to be able to extract all our information from just those 4 cycles. But you can see the signal to noise is really very good. And so we have confidence in the information. The initial mass was 150 solar masses. The final mass was 142. And the final spin was 0.72. The gravitational energy loss, therefore, was 8 solar masses. That's quite a big punch of energy being released all at once. The spin is not an observed parameter. The spin is inferred from numerical simulations of the merger. So there's evidence again for precession and for non-zero spin. And the thing I want to point to here is that there's a ring down that we're seeing. We see the peak, which is the merger peak, and then we see cycles after the merger peak. That's the ring down, the black hole settling down into a nice smooth curve black hole. And this is about the clearest picture of ring down we've ever had. And I'd like to make the point that this is the way you identify, really clinch the case for having a black hole. And not some exotic star composed of bosons or something else, because the normal mode structures of material systems are going to be different from the normal mode behavior of a black hole. And so this is a pretty convincing case that we're actually seeing the black hole. Now, the most intriguing part of this story is that there was an optical flare detected by the Zwicky transient facility at Mount Palomar in the same localization area as 190521, which was a very large area on the sky. We didn't localize it very well. And this flare occurred 35 days later. Now, the Zwicky transient facility monitors for transients and finds lots of them. So in that area, there were lots of transients. But this one was special because it really fit a model for the emission that you'd expect from a black hole moving at a reasonable velocity through an accretion disk around a supermassive black hole. And so the suggestion is that what we saw was 2 two black holes in the neighborhood of a supermassive black hole, not far from an accretion disk. Maybe even they were encouraged to merge because of the gas that was present. And there was a kick that's expected, especially when there are asymmetric masses. So the black hole goes off with a kick, and that kick happened to take it through the accretion disk at a supersonic speed, and it made the whole thing light up. And so that's a really interesting possibility. There's been a lot of debate about whether that's a viable model or not. And again, it's one of those things that we may never really know, but it shows you what exotic systems we might be seeing. Now, if I continue with this, I'll talk about the upper mass gap. This is the one that, because of its large mass, that has two black holes that are in that upper mass gap, or one of them very close to it anyway. The 66 and the primary was certainly in the middle of it. So it raises questions. If we of course, maybe we don't understand why this pulsational pair instability that would blow the star up. Maybe we don't understand that so well, or maybe both of these black holes were formed by mergers of other black holes, of the kinds that we've been detecting all along, producing merger remnants that are already quite massive. And then those mergers got together. Well, how could that have happened? Was it in a quadruple system? Was it in a cluster? There's possibilities here, but intriguing ones. And again, I don't think we have convincing answers. GW 1908-14 is the last of the list of four that I wanted to talk about individually. The biggest mass ratio. I talked about the asymmetric one that had a mass of 3:1. Well, this one has a mass ratio of 9:1. It was detected very strongly. It's at 240 megaparsecs. So it's secondary with this mass of 2.6 solar mass. This is smack in the middle of this lower mass gap. It's too heavy to be a neutron star as far as we understand the physics of neutron stars, but that's probably not very secure. It maybe is a bit heavier because it's spinning very fast and hasn't lost its spin, which would imply it doesn't have a very strong magnetic field. Or it might be a really, really small black hole that was maybe formed by the merger of two neutron stars and just came out as a remnant of 2.6, and then it found itself merging with another black hole. So there's a whole lot of possible histories here, but we've certainly seen this object in this mass gap, and we can't even claim what we've seen. The orbit had a clear detection of higher modes, and I mentioned that that allows you to get a much better value for the distance. And in this case, that also allows us to combine this to estimate the Hubble constant. We had our own measurement of the Hubble constant with GW 1708-17, and if you combine that data with the distance measurement and that we have here, and the possibility, so you have to get velocities, but we have a reasonable size error box, and there's only a certain number of candidate galaxies within it, so you average over those galaxies to get a velocity. And that gives you a somewhat improved value for the Hubble constant, and it's still in the same ballpark as the one we had before. So I'll be talking about Hubble constant a bit more later on, but this is an interesting thing that this particular one, because it's so asymmetric, gives a pretty good distance. So there's other a variety in this catalog that didn't result in detection papers, separate detection papers, but I'll just point out a couple of them. GW 190426, 152155 is a possible neutron star black hole merger, and that would be the first one that we have any confidence in as a neutron star black hole, and that people are still looking at that. We'll hear more, I think, from the collaboration on that as time goes on. There's GW 190924, 021846. It has a total mass of about 16 solar masses. Both objects are bigger than 3 solar masses, so they're both black holes. So it's actually our lightest binary black hole in the whole observing time so far. I haven't talked much about spins, but we try to estimate the spins. We get a bit of information from the end phase of the orbit, and we're looking for large spins because that gives us interesting histories. And we're looking especially for anti-aligned spins. We'd love to find anti-aligned spins. We haven't any convincing candidates yet, although there are some. There's one that has a preference for being anti-aligned. Anti-aligned spins are disfavored if the system is made from 2 binary stars that have a long evolution history together. So they're probably capture candidates from clusters. This is a picture you've probably seen in various forms over the past years, where we describe all the black holes that we've managed to detect. And right here up at the top is that very most massive system that has pushed us up to near 160 solar masses for the largest black hole we've ever identified. Then we have the neutron stars down here. And you can see that all the black holes that we're detecting, practically all, are heavier than the electromagnetic black holes, the ones that are found in X-rays. Now we're starting to push into the mass gap here, also above wherever we see the neutron stars in the electromagnetic system. So there's a lot more challenge here to stellar evolution. Looking back on this, what is it that we see now that gravitational waves are able to tell astronomers? A lot of this was expected, but now we're seeing it happen. First of all, that there's lots and lots of black holes, a lot more black hole binaries than were anticipated. We're telling them about the masses of the binaries, which turn out to be much higher mass black holes than were anticipated, and make the X-ray binary black holes look a bit unusual. We're giving a bit of spin information, and we're going to be getting that better and better as time goes on. We're giving sky positions, so possible associations with galaxies, which has a lot to do with the merger history and the formation histories of these systems. We're talking about we're able to deduce information about the neutron star radius when we have binary neutron stars. And that, of course, feeds in to understanding the equation of state. Then we get the distance, which feeds in then to estimates of the rate of mergers per unit volume. And that's an important aspect that informs stellar evolution. The distance also allows us to get estimates of the Hubble constant. These last 3 are I'm highlighting because they benefit from the statistics. The first 4 are basically things about individual systems, but as we get more and more systems, we get better and better information about these last 3. So looking ahead now in the near future, well, the near future involves, the first thing will be release of the analysis from observing run 03B, the second half of 03, which started in October and finished at toward the end of March, a few days prematurely from when it was supposed to finish because of COVID. That data is being analyzed. The updated catalog can be expected at some point. We'll see from that improved statistics on rates, and also there'll be a paper on estimating the Hubble constant using dark sirens, using all the black hole systems that we've seen. No electromagnetic counterparts to any of these mergers have been claimed by astronomers, despite the fact that some of the binary black hole localizations have been very good. So that's probably not a surprise, but a disappointment after GW 1708-17 showed us what we can really do when we get a good counterpart. There are 56 candidates in the list that were announced during the 03B run. So this is the public data, 56 candidates. If we go through the list, some candidates were withdrawn afterwards. This is only the ones that still remain. If we go through the list and look for candidates that have whose nature has been estimated from the parameter estimation of the system at confidence levels better than 80%, then we have 4 systems in the lower mass gap. So the 2 systems that we've already seen, not so unusual. We're seeing more systems in that mass gap, and it's going to raise real questions about what is that gap. We're seeing 2 more binary neutron stars with better than 80% confidence, and 3 systems that appear to be neutron star black hole systems with 80% confidence. So finally, we are seeing neutron star black hole systems. Now these have to be analyzed, and we'll be seeing individual papers and collective papers on these. And some of these candidates may not be, may turn out on further analysis not to be very secure. There may be other candidates, other detections added as the data is reanalyzed offline. So the 56 is only a tentative number. Interestingly, there was one 03B candidate that was found in a burst search, and it doesn't appear to be a binary system. It didn't turn up in any of the binary search pipelines. So this one is called S200114F. That's the way we name the candidates before we classify them as real detections. It could still be a binary in the intermediate mass black hole region, because as the mass goes up, the number of cycles we get goes down, and so it may be that we just got 1 or 2 cycles at the end of a merger, or it could be something much more exotic, and so that's going to be that's something people are really looking at very hard. If we look at the middle term future, that is the decade of the 2020s, COGRA has already joined the network, did a coincidence run with GEO. It was just at the end when things were shutting down, but GEO kept running. GEO can run unattended, and so it was able to do a coincidence run with COGRA for about a month. LIGO, Virgo, and COGRA are now planning to resume with observing run 04, but only after June of 2022. So we still have more than a year and a half to wait before we get new data. This has been delayed by COVID-19, but also by procurement issues, which themselves have built-in delays because of the pandemic. But I hope that the sensitivity will improve again, and we'll be getting closer to the target sensitivity, the goal for advanced LIGO. After that, and perhaps another upgrade and an 05 observing run as well, we can look ahead at what's called A+, which is an upgrade of advanced LIGO that's now funded and it's under development. And so that'll come in with hardware upgrades at some point have to be a decision about when that happens, but hopefully it'll become operational around 2025, 2026. I hope the COVID hasn't put in more of a delay on that. And the great thing is LIGO-India is expected to join with A+ sensitivity around that time. And you people at IUCAA know much more about that than I do. What we expect with this enlarged network of observing is much better sky coverage. There's large parts of the sky at any one moment that we don't get good sensitivity in, but with CAGRA and with LIGO-India, we would expect much better sky coverage. And we get much better rejection of glitches and so on, so that we can get much closer to the Gaussian thresholds that we should be operating at. And that lowering the detection threshold gives us a lot more distant events. It gives a lot weaker events, but they do contribute to the statistics, and they are very interesting in themselves. So we should be expecting much higher event rates. So what would we be expecting in the decade of the 2020s in terms of the science? Well, event rates are probably averaging more than one a day. This extended Hanford, Livingston, Virgo, CAGRA, India network will really, I think, begin to describe the populations of binary neutron stars, black holes, and neutron star black hole binaries, their masses, their spin distributions, and tell us about the mass gaps. Tell us whether those mass gaps are real or what's in them. So this is the decade, I think, where we get a lot of information of that kind from the statistics. And we should expect big revisions in what people used to think about stellar evolution and binary evolution scenarios. But also insight into other ways of forming binaries, binary formation modes from clusters and from triples and so on. The nuclear physics in neutron stars is going to be much better pinned down. I think we're really going to, by the end of the decade, we're really going to have an understanding of what the equation of state of neutron stars is, which will have strong ramifications for strong interaction theory, and will end a lot of mysteries also in pulsar theory and other aspects of neutron stars, supernova theory, all sorts of things. We're going to almost certainly see gravitationally lensed systems. Gravitationally lensed transient systems are systems which appear in the same place in the sky because our direction finding isn't so good. So they'll be looking like they come from the same place, but they'll come at different times because they'll travel on different paths. And gravitational lensing always has an odd number of images, and therefore, in principle, if we have a gravitational lens system, there'll be 3 events, not just 2. But one of those images is demagnified, and it might be too weak for us to detect, but people will look for it. So it could be another way of measuring Hubble constant. People are measuring Hubble constant now with gravitational lensing and modeling gravitational lensing, and modeling gravitational lensing for gravitational waves may also be an interesting way of handling these things. Will we detect gravitational wave pulsars? This has been a favorite subject of mine for a long time, and we are getting better and better upper limits and pushing things down. The computational demands are overwhelming, but with computers getting better through this decade, and with more data from more detectors that can eliminate spurious lines in the spectrum and so on, maybe we're going to find some GW pulsars. And also exotica, primordial black holes, cosmic strings maybe. The primordial black holes, if there are stellar mass primordial black holes, maybe we'll be able to get some evidence for that. I want to mention the Hubble constant tension. I've talked about the Hubble constant a lot. I think most of you probably are aware that despite the fact that we're getting in really accurate measurements of the Hubble constant now, it's we're getting two groups of data: the local ones from supernovae, from lensing, from other things in the near part of the universe, give higher values of the Hubble constant than the ones we get from the cosmic microwave background. So if that's a real discrepancy, and the error bars are now like 5 sigma apart, then we're going to need new physics to understand it. Something has happened to the universe in between that nobody expected. But there's always a doubt that the local methods are maybe prone to systematic errors. The people doing them are very careful about this, but there have to be calibrations and distance ladders and so on. And so our methods may give us another check on that. We don't use distance ladders. We have a different systematics and different calibration methods. And so if we find, as we get better accuracy, if we find that we're consistent with the local values, then I think the case for new physics gets pretty overwhelming. We get to that point where we can make that contribution when we're around the 2% accuracy, which we're nowhere near right now. A paper that's on the archive that came out this year has modeled the possibility of using dark sirens with gravitational wave detectors in various different network configurations, and with the observed binary black hole rates. So dark sirens are ones without counterparts, and so there's always an uncertainty in what is the host galaxy, and that is what is the right velocity to use for the Hubble constant. But you can average over that. And so if you've got a population, you can actually do pretty well. And with this extended network, when LIGO-India comes on with A+ sensitivity, the expectation is that we can get Hubble constant to about 1% accuracy in only 2 years of observing, using just the strongest binary black holes, the nearest mergers. So that's very encouraging. So I just have that to say to the hardware people: keep building LIGO-India and make it work, because working with A+ sensitivity, working with the other two LIGOs, makes a huge difference in the reliability and the accuracy with which you can make these measurements. Also, we might be lucky and get an electromagnetic counterpart to a binary neutron star. But if we rely on the dark sirens and just the statistics that we know we can expect in terms of observing binary black holes, then we don't have to be lucky. We just have to have the right instrumentation and a couple of years of observing. If I look at the longer term future, and this is my last slide, LISA is going to launch in the mid-2030s, and so I took us up to the end of the 2020s in my last few slides. And it's going to be very exciting because it will peer right through reionization. So it'll give us the first look at what the universe was like at redshifts of 10, 15, wherever there are black holes that are merging together. It's going to put constraints, I'm sure, on the dark energy equation of state. It'll show how, probably tell us how the supermassive black holes that we see in so many galaxies actually started forming. And it'll test GR to amazing precision and more. And then after that, I think we'll be expecting, and I hope that they'll be funded, the so-called third generation ground-based detectors, the Einstein telescope in Europe, Cosmic Explorer in the US, and maybe other places. They probably arrive in terms of their observing coming online toward the end of the 2030s. Every binary neutron star, every stellar binary black hole will be recorded. every merger will be recorded by these systems. They really take us out right to the edge of the observable universe for binary neutron stars. They'll detect coalescences of systems that were originally detected by LISA. LISA will give a prediction. This system is going to merge on a certain day at a certain location in the sky, and ET and cosmic explorers can go and have a look at that, pick that up. So that's going to be a very interesting new kind of science, higher precision gravitational wave science. And so have a look at the white papers that I've listed there on ET and look at the science that's going to be coming. And apart from a sentence a minute ago, I haven't even talked about testing general relativity. I wanted to focus on the astrophysics here. It's a whole different talk about the testing of general relativity and the other hints of fundamental physics, but we are doing something with general relativity that we can't do any other way. And so the fundamental physics aspects of this are also going to be very exciting. So I'll stop there, and thank you very much for your attention.
Thank you very much, Bernard. Thank you so much. And what a great overview of the 56 surfaces so far, and so much more to do. I'm sure you have a lot of questions. We have a participant list of more than 100 between here and YouTube right now. And I'll ask people to raise their hand using the raise hand option in the participants window. We already have quite a few questions coming up. I'm unmuting you. Indranil, you're first. Go ahead.
Thank you. It's a very good talk. I have a very simple question. Since LIGO actually showed us that to build, intermediate mass black holes, we need merger of stellar mass black holes. So what is your take about forming supermassive black holes at the centers of galaxies?
Thank you. Thanks very much for listening. And I think what we're seeing with the intermediate black holes is we're seeing that we're starting to see that that region is populated, that part of the mass scale is populated by systems that come from below, hierarchically emerging. It doesn't mean that's the only way you can put systems in there, and there's still the open question of whether early on in the universe, gas collapse with very low metallicity clouds might have produced black holes straight from collapse at that in that mass range, or even above the 150 that we saw, maybe up to 200 or something. So there are other ways, probably other ways of forming it. The question for the supermassive black holes is, did it happen early enough? Anything that gets into that mass range could be a seed for a supermassive black hole, either through further mergers, if it's in a cluster or it encounters other black holes, or through gas accretion. It can be a seed for a supermassive black hole, but it has to happen early enough in the universe. And so we're seeing systems now. We saw this huge merger at redshifts of redshift 0.8. Well, did these mergers also, were they happening also at redshifts of 15 or something like that? That's a question that probably Lisa might be capable of answering. Maybe ET will be able to answer that, but we don't know yet from what we've seen. So I think it's still early days. I don't think it changes the picture of evolution of supermassive black holes all that much, because there's so many uncertainties yet. We're just picking up one side of the blanket and trying to look under it, but there's a lot more to be seen.
Thank you.
Thanks. I suppose it's early days. Next, let's go to Shantanu. Shantanu, I'm unmuting you.
Yeah, so thank you. Very nice talk. So I just want to ask about a source which is not discussed much. So in Steve Weinberg's 1972 textbook on GR, he talks about gravitation waves from thermal Bremsstrahlung processes in the sun, but the estimate he gives is very pessimistic, 10 to the minus 37 or so. Do you think we can detect this with ET or beyond that?
That's interesting. I haven't thought about that for a very long time. I don't think that is detectable, even with ET. And I don't even remember what the frequency range was, but I suspect that that's pretty much out of range for anything that we're likely to be able to detect. Yeah, the sun isn't a great place for generating gravitational waves.
Okay, let's go on to thanks. Let's go on to Sanjeev. Sanjeev, are you there? I was trying to unmute you.
Okay, so Bernard, so you have given us a very nice tour of the highlights of the last 3 runs of LIGO, Virgo, and so on. And now I think there are all these possibility of 5 detectors coming up in the next in this next decade. So, what do you think? Which do you think would be the next source besides black hole binaries? You know, I mean, or neutron star binaries which have been detected. Which do you think would be the next source that would be detected? And also, do you have any thoughts on unpredicted sources which have not been seen at all electromagnetically, which could be detected by these 5 detectors?
Hello, Sanjeev. Really nice to speak with you this way. Yeah, you've asked me to bring up the crystal ball. I think in a way, it's kind of surprising that binaries have totally dominated everything that we've detected so far. And I certainly think that we can't be very far away from detecting our first gravitational wave pulsar, that is the CW searches. And I do think that having multiple detectors, even though all you have to do is analyze one detector's data stream, multiple detectors can veto spurious candidates, and people are already starting to do that. And I think we're just in need of a bit more sensitivity combined with a bit more computer power, perhaps. So it wouldn't surprise me if that was the next source that we find. Although, pretty reliably, I'd say, there's a very good chance that we'll also detect stochastic gravitational radiation.
Yeah.
It won't be the fundamental kind that came from the Big Bang. It'll be astrophysically generated by the binaries that we're seeing, actually. So that won't be too big a surprise. But we probably have a very good chance of getting to that to enough sensitivity level to pick out that stochastic background. But to me, it'd be very satisfying if we could find a CW source. And then as far as your question about what we don't know is, well, I don't know. The cosmic strings are often lumped in with things that we don't know and haven't been predicted, but of course they have been predicted in some ways. That is, we understand how to look for them. It would be great if we saw a signal that we thought came from a cosmic string. But there could be other kinds of defects out there, cosmological systems, cosmological sources that arose in the very early universe. And that would be really exciting. I think that would be one of the most fantastic things we could possibly do.
Okay, thanks.
Great.
Thank you.
Trust Sanjeev Dhurandhar to try to catch you on the back foot there. I mean, try. Shrikanta next. Shrikanta, go ahead.
Hi, Bernard. Thanks for
Hello, Shrikanta. Very nice to talk to you here too. Yeah.
Yeah, likewise. We wish you were here because we could have taken you out for dinner and then asked a dozen.
Oh, gosh, my stomach is rumbling already.
I'll limit myself to two related ones on the stellar, population synthesis, which you alluded to. There were those days before the gravitational wave detections when there were all sorts of predictions on rates, right? More binary black holes or more binary neutron stars. But as you said, the landscape is now shaping up. And perhaps we are robbing Peter to pay Paul. Maybe we are forming more binary black holes at the cost of perhaps less binary neutron stars. Do you think that is settling down, or the jury is still out? Maybe you're speaking to more of these stellar population modelers. What do they say? What are the prospects of finding binary neutron stars? Will they be still at the rate of maybe one a year, or is there a chance of that rate improving? Eventually, of course, I'm getting at neutron star equation of state, another thing you have alluded to. So stellar population synthesis on one hand, neutron star equation of state on the other hand, with more BNS observations perhaps. But finally, the second question is, how would NICER complement things, if you could tell us?
Oh yeah. Okay. So on the rates of binary neutron stars, well, in the old days we used to say one of order one per year out to a distance of 100 megaparsecs, and now we've seen that the sensitivity that we've been running at is about a BNS range of about 100 megaparsecs. So we're getting a handful of events, and so I think the rate is not very different from the rates that we expected from the binary pulsar population in the galaxy, maybe a little bit higher. But what is what is happening is, we had one that I just mentioned that was at a distance of 240 megaparsecs. We're missing others that are at 100 megaparsecs because they're outside of our antenna pattern. So they're not in a part of the sky that we can see at the time it happens. And so as you know, the distance of 120 or something for Livingston is an average distance that takes into account the fact that the antenna pattern doesn't cover the whole sky and all of that. So I think we are not too off the old estimates, and we're not challenging very much the binary evolution scenarios. What I would love to see is the ability to find counterparts, and that's something that we have to rely on the optical astronomers and the X-ray astronomers and the gamma ray astronomers. I think the Vera Rubin telescope is going to make a difference to that. I think we're going to be able to see the afterglows at much higher distances, and that's the most reliable way probably of getting the counterpart. So I think when LIGO-India comes online and we have all sky coverage and we have the instruments like the Vera Rubin telescope, then I think we're going to get a real population. So that's something really to look forward to.
Right, and any thoughts about NICER complementing GW?
Yeah, I don't know that much about NICER, but it certainly complements on the physics, on getting at the structure of a neutron star and getting right down to the surface of the neutron star. It's been very impressive data. So I really look forward to much more of that from NICER. Yeah.
Thank you.
Thanks, Bernard. There are many other hands coming up. I hope you can answer a few more.
Okay, I'll try to be quick.
Okay, so no, that's all right. I mean, we have plenty of time, but I knew that there would be quite a lot of interest here. I'll just relay a question from the YouTube. There were about 40 people there.
Oh yeah.
Monit Chakraborty is asking, we see the mass distribution in your plot of the GW detected black holes to be quite different from the electromagnetic ones, the ones from X-rays. But is there anything known about the difference of spin of these two populations at all?
The difference in spins, we don't have great information about spins in most of our systems. And that's, as I said during the talk, that's because we only get the spin information in the last couple of cycles, last few cycles of the merger. As we improve sensitivity, and as we'll get better spin information, I think what we can look forward to is not so much a survey of what the spins are, but we can look forward to individual systems that are nearby and quite strong, where we can really pin down some of the spins and discuss those individual systems. But whether they're going to be typical, whether they're going to give us a big survey of spins, I can't answer.
Yeah. Also, I don't think we know much about the spins of the X-ray detected systems either. So,
no, not the X-ray, not those. There is. We obviously with the neutron stars that we see, the pulsars, we know their spins, and we know most of them are relatively low spin in terms in the measures that we're using, but we don't, even with the binary neutron stars, we don't have very good information yet.
I'll ask Kandu to unmute. I mean, the co-hosts cannot raise their hand. Kandu has been wanting to ask a question. Go ahead, Kandu.
Hi, Bernard. Very nice overview of all the detections and
Thank you.
events. I was wondering about this comment that you had about gravitational lensing, then using that to measure H0. And I mean, from my very old things about lensing, which I did long back, the time delay will be for galaxies about a years. For stars in the galaxy, maybe, still quite long. Unless you have something very small mass, which is in between or something like that. So people, I mean, I thought about long back, but you have to then correlate signals over many far apart in time, right? Or are you thinking of something else?
No, far apart in time. Okay. And people have suggested, even it was raised during 01 that some of the black hole, the detections we might be making would be lensed counterparts of the first one that we saw. People are alert to this and looking all the time. In the paper about the very massive one, which produced the 150 solar mass black hole, or 140. There was a statement in that paper that we do not think that was lensed. In other words, that it was brighter. It was made brighter by lensing. So that's the two aspects of it. You could have individual systems that are just brighter. There's no other image. And the claim was that it's unlikely that it was significantly brightened by lensing.
Yes.
But we do know that's going to be happening. But having multiple images, people are on the alert. It will be very exciting, and I'm sure it'll happen at some point. With, as you say, time delays of order a year or so. Yeah.
Okay, nice. Thank you.
Great. Suruth, go next.
Yeah, Bernard, thanks for the great talk summarizing these results. My question was related to Hubble parameter estimations from dark sirens. Do you think we can safely benefit from statistics, or is there a systematic floor to worry about before we hit the percent level sensitivity?
I think the dark sirens are remarkably systematics free. That is, there's one aspect of them, which is of course the selection effect, that the ones that are face on are going to turn up more often or at larger distances. So our sample set will be improved by will be dominated by the face-on ones. Those are the ones that are hardest to get a good distance for, because that's where it's hard to decouple the inclination the measurement uncertainty on inclination from the Hubble constant or the distance measurement. So that's a known selection effect, and that's just folded into the Bayesian priors. So because they're selected just because of the gravitational wave signal. They're not selected for any other reason. So that's pretty much free of systematics. The systematics I worry about more are in the calibration of our detectors, the sensitivity of our detectors. When we push down to 1%, that's achievable, I'm told, by the calibration teams with the methods that are being used right now, but it does push them. And so that's something we have to be very, very careful about, because a calibration uncertainty is a systematic that will not average out with large populations. So does that answer the question?
So this is related to like doing cross correlations with galaxy catalogs and so on, right?
It is, and so you get a number of candidates within your
right.
field of uncertainty, and each one basically gives you, and of course it could be that some of the systems are not in galaxies anymore, or
right.
they're in such minor galaxies that we don't even notice them. They're not in the catalogs. So yes, there's the catalogs. If the catalogs are incomplete, that's a big problem, and that's going to be an issue that people are addressing again. But that's going to be improved by the survey telescopes that are coming. I think at a 1% level, the nice thing is that when you get to 1%, you eliminate almost all the candidates in your field, because that's a pretty precise measurement, and so as the statistics build up, it gets better and better. I think it gets easier to add new candidates in.
Mm. Thanks.
Great, thanks. I hope you can take one or two more. Is that all right?
Sure.
Yes,
sure, no problem.
So, yeah, okay. Thanks. Indulekha, go ahead, please. You're next.
I have two questions actually. One is regarding the Bayesian prior regarding the initial masses. Is it drawn from the standard IMF, or does it have the choice of prior have any influence on the parameters like spin, etc.? The other question is regarding if once we have LISA and HLVKI up, can we use these observations to fix the local standard of rest? Thank you.
Very interesting questions. You're absolutely right. The values that we get, the distributions we get for the masses of systems depend upon the priors, and depend upon therefore what we take, how much information we think we should put in. I'm not very well versed in that. That's something that the parameter estimation group does worry about. I think the numbers that are published take into account two kinds of uncertainty in priors, if I could express it that way. One is what you're referring to, but the other one is our waveform models, because we estimate parameters anyway by fitting to waveform models, and our waveform models are approximate. They're meant to be a good, faithful representation of the waveform over a wide range of parameters. So they don't fit any one waveform exactly. And so there are biases there. And so we have, depending upon what problem you're looking at, you might have 3 or 4 different waveform families that would give different values for the masses. And in the papers, so in the numbers I've quoted are pretty crude looks, but in the papers, of course, you often find tables with different parameter estimates depending upon which waveform family you want to take, and that gives you a better idea what the systematics might be and what the uncertainties might be. But beyond that, I can't really address the question of the priors on the mass distributions. But that is an important question. Could you repeat the second question, please? Yeah,
what I asked was with LISA and HLVI operative, can we use the simultaneous detections and localization in the sky to fix the local standard of rest?
That's a question I've never thought about. It's true that when Lisa's flying, we probably won't still have ET in 3rd generation, but we will have at some level of sensitivity, hopefully good sensitivity, the existing ground-based detectors, and they can do a lot on these systems that are seen by both LISA and by the ground-based. The LISA information can really help pin down the directionality, and also that long time span can help pin down the other parameters extremely well. But I haven't really thought about the local standard of rest, so that's an interesting question. I take it you are thinking about that in terms of your own research.
This came up in thinking about pulsar detections. So there is this problem of fixing the local standard of rest. And in their discussions, it came up that if we had sufficiently separated detectors for radio waves, radio pulsars, you could fix the local standard of difficult.
Very interesting. Very interesting. Yeah.
Wondering whether gravitational wave, detectors could solve the problem.
Yeah. Very interesting. Maybe that's worth investigating. Yeah. Very good point.
Thanks, Indulekha. I'm actually tempted to stop the discussion, even though the hands are coming up. Shantanu's already had a chance. Let's give Sanjit a chance, and then we'll stop today. Sanjit, go ahead.
Thanks so much.
Yeah, very nice talk, Bernard. Yeah, just you covered everything about the astronomical sources and so on. Just one thing was missing, so I thought I will ask you. What is your take on supernovae?
Yeah, I didn't say anything about supernovae. Well, our range right now is to the local group, so we could get lucky. When we get to ET, we can get out to Andromeda and other nearby galaxies, and so yeah, in that period of time, with one supernova every 30 years or something in a galaxy like ours, whatever the rate is, we're probably going to get something like that. Yeah. I think that would be also extraordinarily interesting, and the great thing would be to be able to couple that with neutrinos, which we can do if it's in the local group now. But if we extend our range out to Andromeda, I'm not sure that the neutrino detectors will keep up with that. So we might not get the neutrino signal. I'm not sure.
Yeah, so 87A we would have detected, I suppose. No?
Yeah, that's right. Yeah.
Shantanu, go ahead. Since Sandeep was quite quick, we can have one last question.
Okay, so throughout, okay, this is related to the last bullet point. So I guess throughout the talk, you use the moniker black holes, but do we really, like, how does, I mean, do we really know that they are black holes as opposed to, I'll give 3 or 4 alternatives when considered, that they are not naked singularities, wormholes, maybe gravitational Bose-Einstein condensate gravastars, and what string theorists have been now pushing for 5 also. So I guess the quick question is, do we know for sure that these are really classic black holes and not one of these other 4 alternatives? And if not, by ET we'll know for sure.
Yeah, this is an important question, and it's one reason that when Kip and Barry and Ray got the Nobel Prize, they were not given the Nobel Prize for identifying, proving that black holes exist, because just the merger doesn't prove it to you. The one thing I mentioned in my talk was the ring down, and I think that is the discriminating thing. I think the way you identify any astronomical system best, that to say that you know what it's composed of, is if you can see it dynamically, if you can see how it behaves dynamically. And so when we see the ring down, we're seeing exactly a classic prediction of ring down from the numerical simulations and the analytic studies of black holes. So we haven't been seeing the ring down very accurately before. We are seeing it in this one system. We are seeing it pretty accurately, and so I think that is getting to be convincing about the nature of the object. But of course, it's then the shoe is on the other foot. It's then up to the Gravistar people and so on to tell us what the ring down signal would be in those cases, and I suspect they'd be quite different, actually.
Thanks very much. Thank you so much, Bernard, for not only giving us a fascinating talk, but staying with us for another half an hour, answering so many questions, and really applauds from all of us. The Zoom doesn't really allow for a resounding applause, a standing ovation.
Right.
So there you are. Thank you so much.